Welcome to the Curious Voyager. It's lovely to have you here tonight. Before we begin, let me ask you something, the way I always do. Where in the world are you watching from tonight? Somewhere the sky has already gone dark, I hope. Somewhere with a blanket, or a soft pillow, or the low, warm glow of a lamp you haven't quite turned off yet. Maybe you're lying in bed. Maybe you're on a couch with the day finally behind you. Maybe you're on a train or a long, quiet drive, watching the world blur past a window. Wherever you are, and whatever hour it is in your corner of the night, I'm glad you found your way here. And if you enjoy these slow, gentle journeys, and you'd like more of them to drift off to, a quiet like and a subscribe genuinely help this small, sleepy little channel keep going. Small creators like me really do rely on that. And to those of you already subscribed, already part of these nightly wanderings, thank you. Truly, you're the reason there's a next one. Now, settle in, get comfortable, let your shoulders drop away from your ears. You don't have to do anything tonight but breathe and listen. And let the ideas come to you at their own unhurried pace. I'll try, as always, not to make this so interesting that it keeps you awake. But if it does, well, at least you'll have learned something lovely. A fair trade, I think. And here's my promise to you, the one I make at the start of every journey. We are going to move slowly tonight, softly, one small idea at a time, with plenty of room to breathe between them. There's no test at the end. There's nothing you need to hold on to, nothing you have to grasp, no equation you must understand. If your eyes grow heavy, let them. If you drift off somewhere in the middle, that's perfectly fine. The ideas will still be here when you wake. They're not going anywhere. This is not a lecture. It's more like a long, quiet walk with a friend who happens to find the universe fascinating and who's happy to point at the strange and beautiful things along the way, and just as happy if you fall asleep against their shoulder halfway through. So, let's begin, shall we? I want you to picture something very small, smaller than you might expect for a story that ends up inside distant planets. I want you to picture a single drop of water. Just one. The kind that might gather at the lip of a tap and hang there, trembling, catching the light, before it falls. An ordinary little bead of water. There is nothing remarkable about it. You have seen 10,000 of them. You are, yourself, mostly made of the same stuff. Now I want you to imagine that this single drop of water is placed very carefully between two diamonds. Not diamonds in rings, not diamonds for wearing. These are gemstones chosen for a different kind of beauty entirely. They've been cut and polished and set into a device with a name as blunt and honest as the thing it does. It's called a diamond anvil cell. And it is exactly what it sounds like. Two diamonds brought face to face with the tiniest sample of something pressed in the gap between them. And then those two diamonds are driven together, slowly, with tremendous force, until the little world trapped between them is squeezed harder than almost anything on the surface of the earth is ever squeezed. There's a reason it has to be diamond, and we'll come back to that because it's a lovely reason. But for now, just hold the picture. A drop of water, two diamonds, and a pressure beginning to build. At first, they squeeze the water to somewhere between 1 and 2 gigapascals. Now, a gigapascal is just a unit of pressure, the way a mile is a unit of distance. And you don't need to feel anything precise about the number. But let me give you a way to hold it. 1 to 2 gigapascals is already something like 10 to 20,000 times the weight of the atmosphere pressing down on you right now. Think of it this way. Above your head, at this very moment, there is a column of air reaching all the way up to space. And it has weight, and it presses on you gently and evenly across your whole body, and you've simply never noticed because you were born into it. That familiar sea of air. Now imagine 10,000 of those, stacked and concentrated onto a droplet no bigger than a grain of rice. That's just the beginning. That's the warm-up. That's the diamonds getting a grip on the water, settling it, holding it still, before the real thing happens. Because then comes the laser. Once the water is pre-compressed and waiting between the diamonds, the experimenters fire a burst from an enormous high-power laser at it. Not a gentle beam, a flash of concentrated energy that slams into the sample and drives a shockwave straight through it. And in that instant, in a shockingly small sliver of time, the pressure doesn't just rise. It leaps. It rockets from those 10 or 20,000 atmospheres up into a range that is almost impossible to picture. The shock spikes the pressure to somewhere between 100 and 400 gigapascals. That is 1 million to 4 million times the pressure of the air around you. And at the very same moment, the temperature erupts too, soaring to somewhere between 2,000 and 5,000 Kelvin. Thousands of degrees. Hot enough to make rock run like water. Hot enough to glow. And all of this, the leap in pressure, the eruption of heat, the strange thing that happens to the water because of it, all of it exists for only a few billionths of a second. Let that number sit with you for a moment, because it's one of the quietly astonishing parts of this whole story. A few billionths of a second. Not seconds, not even a fraction you could blink in. Billionths, the entire event, the creation of something the universe hides deep inside planets, flickers into being, and vanishes again faster than light itself could cross the room you're sitting in. If you tried to watch it, it would already be over before the thought finished forming. And yet in that impossibly thin slice of time, between two diamonds, at the touch of a laser, something extraordinary happens to that ordinary drop of water. It becomes a kind of ice. Now, I know, I can feel you turning that over. Ice at thousands of degrees? Ice, when we've just set it hotter than molten rock? That word doesn't seem to belong here at all. And you're right to notice that. Hold on to that little snag of confusion, that sense that something doesn't fit. Because that snag is the whole heart of tonight's story, and we are going to smooth it out very slowly, very gently, until it makes a strange and beautiful kind of sense. We won't rush it. We have all the time in the world. But let me at least tell you what happened to that water. Let me tell you what it actually became. Because this is the part everyone gets slightly wrong, and the truth is more elegant than the shorthand. Water, as you know it, is made of very simple pieces. Each little molecule of water is one oxygen atom holding hands with two hydrogen atoms. That's the whole recipe. One oxygen, two hydrogen. That's the H2O you've heard about your entire life. In the water in your glass, these little three-atom molecules tumble and slide and bump past one another freely. And that tumbling freedom is what makes it liquid, what makes it pour and splash and take the shape of whatever holds it. And when you freeze that water into ordinary ice, the kind that clinks in a drink, the kind that forms on a winter window, those little molecules stop tumbling. They lock into a neat, orderly, repeating pattern, a lattice, a scaffold, each molecule holding its place in a delicate crystal. That stillness, that locking into place, is what solid means. The pieces have stopped moving and settled into a fixed arrangement. Liquid, the pieces flow. Solid, the pieces hold still. That's the whole of it, really. That's what we mean by those two words. Which pieces are moving and which pieces are staying put. So now, here is the strange and lovely thing that happens to our droplet under all that pressure and heat. Here is the thing that was predicted long before anyone could make it, and that nobody had ever actually seen until very recently. The oxygen atoms freeze, and the hydrogen atoms melt. At the very same time, in the very same substance. Let me say that again, more slowly, because it deserves to be said slowly. Under those millions of atmospheres, the oxygen atoms lock themselves into a rigid, orderly crystal lattice. They stop moving. They stack into a fixed, repeating pattern, a solid scaffold, and the enormous pressure holds them there so firmly that they simply cannot break free, cannot tumble, cannot flow. By every meaning of the word, the oxygen has become a solid, a crystal, ice, in the truest structural sense. But the hydrogen atoms do the opposite. The hydrogen, under that same heat, breaks loose. It tears away from the oxygen it had been bound to, sheds itself down to bare little cores, bare protons, the naked centers of hydrogen atoms, and it begins to move, to wander, to stream through the gaps in that rigid oxygen scaffold, flowing between the fixed oxygen atoms the way water flows through the spaces in a sponge, the way a river runs through a canyon whose walls never move. The hydrogen doesn't just wiggle loose, it flows, it diffuses, it behaves, by every measure, like a liquid, moving through a solid that stays perfectly still around it. And so you have, in one single substance, at one single moment, both states at once. A solid and a liquid occupying the very same space. The oxygen frozen into a rigid crystal, the hydrogen flowing through it like a river runs through stone. Not one turning into the other, not half melted, caught somewhere in between. Both, fully both. A frozen scaffold with a liquid streaming through its bones. This is Superionic ice. That's its name. Sometimes you'll hear it called Superionic water, which is really the same thing said another way. And it has a formal name too, a proper designation the way species have Latin names. It's called Ice 18. Ice XVIII, written with those old Roman numerals. Ice number 18. And in a little while I'll tell you why there's an 18. Why ice has numbers at all, because it turns out that the plain frozen water you think you know is only one member of a very large and very strange family. But we'll get there gently. No rush. For now, just hold this picture, and let it be a little wondrous. A block of ice in which the oxygen is a solid crystal and the hydrogen is a flowing liquid, both at once, the same water somehow frozen and flowing at the very same time. That's not a poet's trick or a figure of speech. It's a real physical state of matter. It has a shape you can photograph, which we'll come to. It's as real as the pillow under your head, and it looks nothing like the ice you know. Here's the next thing that surprised everyone, and it's one of my favorite little details in the whole story. This ice is black, not white, like frost, not clear, like a cube in a glass, not the pale blue of a glacier, black, dark and opaque, like a polished stone, like a piece of coal, like something you'd expect to find at the bottom of a fire rather than at the top of a drink. And when you understand why, it's genuinely satisfying, so let me walk you through it slowly. Think about ordinary ice for a moment. Think about a clean ice cube or a sheet of clear ice on a still pond. What does light do when it meets that ice? It passes straight through. You can see your fingers through the cube. You can see the pebbles at the bottom of the frozen pond. The ice is transparent. And the reason it's transparent is that in ordinary ice, everything is locked down and neutral and orderly. The atoms are all in their places, their charges all tidally balanced, nothing loose, nothing free to interfere with the light. So the light just sails through, undisturbed, and out the other side, and the ice looks clear. But now think about our Superionic ice, with all those hydrogen cores, all those bare protons streaming loose through the crystal. Those protons are charged particles. They carry electric charge, and they are moving freely in enormous numbers. And there are excited electrons stirred loose by the heat as well, more little charged things adrift in the crystal. And here is the thing about light. Light is, itself, an electric and magnetic ripple. When light tries to pass through a place that's full of free-moving charges, those charges grab at it. They absorb it. They scatter it, knock it off course, soak it up, and refuse to let it pass cleanly through. So the light can't sail through the way it does in a clear ice cube. It gets caught, and absorbed, and scattered into nothing. And when a material absorbs and scatters the light that hits it, instead of letting it pass or bouncing it cleanly back, that material looks dark. It looks black. The same free-flowing hydrogen that makes this ice half liquid is exactly what makes it pitch black. The flowing and the blackness are two faces of the same fact. The freedom of those little charged particles is written right there on the surface, in the darkness of it. So sit with that image for a moment, because it's a beautiful one and a strange one, and it's the opposite of everything the word ice has ever meant to you. A piece of ice that is black instead of clear, hot enough to glow instead of cold enough to bite, dense and heavy instead of light and floating. A solid you could hold the shape of, with a liquid running silently through the inside of it, frozen and flowing, dark and burning, all at once. And now I want to plant a small seed in your mind, a thought I'll ask you to carry with you through the rest of tonight's journey, because it changes how the whole story feels. It's the quiet idea underneath everything else we'll talk about. We think of ice as clear. We think of ice as cold. We think of ice as something that floats, that bobs on the surface of a drink or caps the top of a winter lake. That floating is itself a little miracle we take for granted. Ordinary ice is actually lighter than the water it forms from, which is why it rises and floats instead of sinking, and that one quiet fact is part of why lakes freeze from the top down and the fish survive the winter beneath. We're so used to it that it seems like simply what ice is: clear, cold and floating. Obvious, natural, the way of things. But what if it isn't the way of things at all? What if the clear, cold, floating ice we know, the only ice most of us will ever touch, is actually the rare kind, the strange exception, the delicate, provincial little oddity that only forms in one very unusual place, a place that's cool and calm and gentle and low, low pressure, a place like the thin skin of a small, rocky world drifting at a comfortable distance from a modest star. A place like here, like Earth, like the glass on your nightstand. Because out there, across the wider universe, water very rarely gets to be cool and calm and gently frozen into clear little crystals. Out there, water is far more often crushed under unimaginable pressures and heated to thousands of degrees deep inside enormous planets, in the vast dark interiors of worlds. And under those conditions, the ordinary conditions of the cosmos, the conditions that are common rather than rare, water doesn't become the pale, floating, transparent stuff we call ice. It becomes this, black, scorching, denser than rock, half alive with flowing hydrogen. Superionic, which would mean, if it's true, and we'll spend the rest of our journey seeing just how true it might be, that we've had it backwards this whole time. The see-through ice in your glass isn't the normal kind of frozen water with a few weird cousins. It might be the weird cousin. The universe's true, default, ordinary ice, the most common form frozen water, takes across all those countless worlds, might be the black, burning, flowing kind that until very recently no human being had ever laid eyes on. The exotic thing made for a nanosecond between two diamonds in a laboratory might not be exotic at all. It might be the most familiar substance in the cosmos, wearing a face we simply never got to see because we happen to live in one of the few cool, quiet, low-pressure corners where water is allowed to freeze the gentle way. I told you we'd smooth out that snag slowly. That's the shape of it, the thing we'll circle back to again and again tonight. Not a magic trick, not a paradox to bewilder you, just an unfamiliar truth, patiently unfolding. That the strangest ice ever made in a laboratory might, in the end, turn out to be the most ordinary ice there is. And that the ice you know, the friendly, clear, floating kind, might be the genuine rarity, precious and unusual precisely because it needs such a rare and gentle place to exist. But I'm getting ahead of our slow little story, and there's no need to hurry. Let's come back to the bench, back to the diamonds and the laser and that flickering billionth of a second. Because before we drift out to the planets, before we go anywhere at all, I want to stay right here in the laboratory with you for a good long while and really look at this thing they made. There's so much more to it than I've told you yet. We've seen that it's solid and liquid at once, and we've seen that it's black. But we haven't yet talked about how astonishingly hot it is while still refusing to melt, and we haven't talked about how, if it lives for only billionths of a second, anyone could possibly know its shape. And we certainly haven't talked about the person who dreamed the whole thing up on paper decades before anyone could make it real. There's a scientist waiting in this story who imagined Superionic ice long before any laser ever forged it, and had to wait 30 years to find out if he was right. So let me pour you a little more of the picture, and let's keep it gentle. Come back to that drop of water between the diamonds. I want you to notice how ordinary the ingredients are. That's part of what makes this so quietly marvelous to me. We are not talking about some rare and precious substance flown in from the far side of the world. We are talking about water. The most common, most familiar, most humble liquid there is. The stuff of oceans and clouds and tears and tea. The stuff that fell as rain outside your window and runs from your tap and fills the very cells of your body as you lie there breathing. Plain water. And the entire strangeness, the whole black and burning wonder of Superionic ice, comes not from any exotic ingredient, but purely from the conditions we put that plain water into. Just squeeze it hard enough, and heat it fiercely enough, and this most ordinary substance in the world transforms into something no human eye had ever seen. Nothing added, nothing taken away. The same water, only crushed and heated into a form it never gets to take down here in our gentle, low-pressure world. There's something reassuring in that, I think, something to carry towards sleep, that the ordinary things around us are not really so ordinary at all. That the water in the glass beside you contains, folded up inside its simple little molecules, the potential to become one of the strangest states of matter in the universe, if only the universe pressed on it hard enough. It's all there, sleeping in the plainness of it, waiting for the right conditions. Most of it will never get those conditions, and so it stays clear and cool and quiet, and that's a kind of gift too. But the possibility is always there. And the diamonds. Let's linger on the diamonds for just a moment more, because I promised you a lovely reason, and here it is. Why diamond of all things? Why not steel, or some tough metal, or any of the hard materials we build our strongest machines from? Two reasons, and they're both elegant. The first is simply that diamond is the hardest material we know of. Nothing else can press so hard without shattering or crushing itself. If you want to squeeze a droplet to 1,000,000 times the pressure of the atmosphere, you need a tool that won't give way, won't buckle, won't be crushed by the very pressure it's creating. Diamond can do that. Diamond can stand at the edge of that enormous force and hold, where almost anything else would fail. So diamond is the anvil, because diamond is the strongest hammer and the strongest surface, both at once. But there's a second reason, and this is the one I find genuinely beautiful. Diamond, for all its hardness, is clear. It's transparent. Light passes through it, and more than that, it's transparent not only to ordinary visible light, but to X-rays as well, those high, sharp forms of light we use to see inside things. So the diamond isn't only a vice for squeezing, it's a window. The experimenters can crush the water between two diamonds and at the very same time look straight through those diamonds to see what's happening to the water inside. Shine a laser in, see the light come back, send an X-ray through, and read the shadow it casts. The diamond squeezes and reveals in the same instant. It's the wall of the cell and the window in the wall, both. The hardest thing we know, and one of the clearest, in a single stone. And that rare combination, hard enough to make planetary pressures and clear enough to watch through, is exactly why a droplet of ordinary water gets crushed between two gemstones and not between anything else. There's a kind of poetry in it. To make the darkest ice, you look through the clearest crystal. Now I mentioned that this Superionic ice is hot, thousands of degrees, and I want you to feel just how much that word should bother you, because the fact that it doesn't fall apart under all that heat is one of the deepest wonders of the whole thing, and we've only brushed past it so far. Think about heat and what heat does. Heat, at bottom, is just motion. When something gets hot, what's really happening is that its atoms are jostling and shaking faster and faster, and that's precisely why heat melts things. Warm are solid enough, and its atoms shake so violently that they break free of their fixed places in the crystal, and the whole orderly structure comes apart into a sloshing liquid. That's what melting is. The atoms shaking themselves loose from their lattice. So heat is the enemy of solids. Heat is what unmakes crystals. Warm anything enough, and it melts, then boils, then scatters into gas. That's the ordinary way of the world. And yet here is Superionic ice, sitting at or above 2000 Kelvin, thousands of degrees, hot enough to glow, and the oxygen atoms simply refuse to melt. They stay locked in their rigid crystal lattice, as if the heat weren't even there. How? How can something that hot stay solid at all? The answer is the pressure. The answer is always, in this story, the pressure. Because while the heat is trying with all its might to shake those oxygen atoms loose from their places, the crushing pressure is squeezing them so hard, packing them so tightly together, that they simply have nowhere to go. The heat says, shake free, come apart, melt, and the pressure says no. Stay, there is no room to move. The two forces fight, heat against pressure, and at these extreme conditions the pressure wins, at least for the oxygen. The oxygen frame holds firm, rigid and crystalline, even while it glows with heat that would vaporize almost anything you've ever touched. It is, quite literally, hot ice. Not hot in some loose figure of speech, not warm ice, not slushy ice. Ice at thousands of degrees, glowing and still a solid crystal, held together by a pressure so vast that even that furnace of heat can't shake it apart. And the hydrogen, meanwhile, in the very same crystal, at the very same temperature, does give in to the heat. The hydrogen, lighter and more restless, does shake loose and flow. So the same heat that the oxygen resists is the very heat that sets the hydrogen free. One temperature, one pressure, and two utterly different answers from the two kinds of atom sharing the same tiny crystal. The heavy oxygen holds. The light hydrogen runs, and that difference, that single split decision inside one substance, is the whole of Superionic ice, the entire strange miracle of it, written in the difference between a heavy atom and a light one under the same impossible sky of pressure and heat. I find I have to slow down here and just sit with it, and I hope you'll sit with me. Because we so easily let a phrase like solid and liquid at the same time wash over us as a clever curiosity, a bit of trivia, and move on. But when you look closely, when you really look, it's stranger and finer than any bit of trivia. It's two different substances worth of behavior happening in one place, at one moment, in one perfectly ordinary drop of water. Simply because we pressed on it the way the inside of a planet presses on everything it holds. The oxygen has chosen to be a crystal. The hydrogen has chosen to be a river. And neither of them is wrong, and neither of them is pretending, and both of them are entirely, physically real in the same black, glowing billionth of a second flake of ice held between two diamonds in a room somewhere on this quiet planet of ours. We'll leave it there for tonight's first stretch, with that image glowing softly in the dark behind your eyes. A drop of water, two diamonds, a flash of laser light, and in the space of a few billionths of a second, the birth of a kind of ice that is black instead of clear, burning instead of cold, dense instead of light, and frozen and flowing both at once. Held together by pressures found nowhere on the surface of our world, and hardly anywhere except the deep hearts of giant planets. And still, we've barely begun. Because a question has surely started to form, quietly at the edge of your drifting thoughts. If this thing lasts only billionths of a second, if it's born and gone faster than light can cross a room, then how on earth could anyone ever know what shape it takes inside? How could anyone photograph a crystal that destroys itself almost the instant it exists? And who was it, all those years ago, who first dared to imagine that water could do something so strange? Long before any laser could prove them right or wrong. Let that question rest, unanswered, for now. Don't chase it. Just let it hang there in the warm dark, like a light left on in a distant window. We'll walk toward it slowly, together, in just a little while. There's no hurry at all. The ice will keep. The planets will keep. And so, I hope, will you, drifting a little further down with every slow breath as we get ready to go, looking for the answer. So let's begin, quietly, with the thing that most surprises people when they first hear about Superionic ice. Not the fact that it's frozen and flowing at once, We'll come back to that. Not the fact that it's black. Not even the fact that it was made in a lab. The thing that surprises people most is simpler than any of those, and stranger in its own way. It's hot. Not warm. Not merely elevated in temperature, hot in the way that lava is hot, or the interior of a furnace, or the air above a jet engine. Near or above 2000 degrees Kelvin, which, if you happen to be drifting off and not particularly in the mood for unit conversions, is roughly the temperature of molten basalt, the dark fluid rock that pours out of volcanoes and glows orange-red in the dark. At 2000 Kelvin, almost everything we call solid has long since surrendered. Most metals are liquid at half that temperature. Steel becomes soft at a few hundred degrees below it. Most minerals we think of as permanent and unyielding melt or decompose in that heat. And yet the oxygen atoms in Superionic ice, the scaffolding of the crystal, the structural backbone of this extraordinary phase of water, do not melt. They stay. Rigidly, locked in their precise, ordered positions in the lattice. A full crystal, a proper, solid, well-organized arrangement of atoms in space, holding its shape through what should, by any ordinary reasoning, be more than enough heat to destroy it. That sounds, if you think about it slowly, almost impossible. And it should. Because by all the intuitions we've built up, living in a world of familiar things, intuitions about what solid means, about what heat does, about the way crystals behave when you raise their temperature high enough, it makes no sense at all. Heat melts things. Heat undoes order. Heat jiggles atoms loose from their neighbors and sends them wandering. That's what heat is, in a deep physical sense, the random, restless motion of particles. Add enough of it, and you pull any crystal apart. So how does the oxygen frame hold? The answer is pressure. Not the gentle pressure of a hand on a tabletop, or even the quite serious pressure at the bottom of the ocean, though that's already several hundred times the pressure you're sitting in right now, wherever you are. Something much greater than that. The Superionic conditions in the 2019 experiment involved pressures in the range of 100 to 400 gigapascals. A gigapascal is already a billion pascals. The atmospheric pressure at sea level, the pressure of the air resting on your shoulders and chest as you breathe, is about 100,000 pascals. So a gigapascal is already 10,000 times that. And 100 gigapascals is around 1,000,000 times the air pressure you're breathing right now. To put that in terms of the planet we live on, 100 gigapascals is roughly the pressure at the boundary of Earth's core. Deep inside our planet, where the rock of the mantle gives way to the iron core, where temperatures are already in the thousands of degrees and the weight of everything above presses down without mercy, that's the kind of pressure the experiment was working with. And the higher end of the range, 400 gigapascals, is several times higher still. We're talking about pressure conditions found essentially nowhere on Earth's surface, and barely anywhere except the interiors of giant planets. Under that kind of pressure, the oxygen atoms are, quite simply, not allowed to wander. The weight of everything pressing in from every direction pins them. It doesn't matter that the heat is enormous. The heat gives each atom energy, yes, makes it vibrate, makes it want to jostle loose. But the pressure wins. The energy isn't enough to push an oxygen atom past its neighbors when those neighbors are jammed in so tightly that there is literally nowhere to go. The crystal lattice survives not because heat isn't trying to destroy it, but because pressure won't let it. And so you get this extraordinary standoff. An oxygen crystal, orderly and rigid and cold in all the ways that matter structurally, sitting at a temperature that would incinerate almost anything else on Earth. Hot ice. not as a metaphor, as a literal description of what is happening. Now, the hydrogen. The hydrogen is a different story entirely, and it's the story that makes Superionic ice what it is. In ordinary ice, the familiar, clear, slightly bluish kind, the kind that clinks in glasses and forms on puddles in winter, the kind formerly called ice H in the scientific literature, ice 1H, where the H stands for hexagonal, in that ordinary ice. Both the oxygen atoms and the hydrogen atoms are locked in place. They vibrate, as all atoms do at any temperature above absolute zero, but they stay put. The crystal is a rigid whole. Everything is ordered. Nothing flows. In Superionic ice, the oxygen stays put. But the hydrogen does something else entirely. When the pressure climbs high enough and the temperature rises to meet it, into that particular zone, a few hundred gigapascals, a few thousand Kelvin, the hydrogen atoms are effectively shaken free. Not from the material, they don't leave. But they break loose from their fixed positions in the crystal structure and begin to move, to wander, to drift through the channels and spaces between the oxygen atoms the way water molecules drift through a porous stone, or the way ions drift through a solution. And here is the precise, careful thing to understand, the thing that separates a real physical description from the shorthand you might read in a headline. The hydrogen doesn't wander as hydrogen atoms in the usual sense. In the conditions of Superionic ice, the temperature and pressure have stripped the electrons away from the hydrogen. Hydrogen, remember, is the simplest atom in the universe, one proton and normally one electron. Under these conditions, the electron is gone, removed, absorbed into the electronic sea of the surrounding material. What's left is the proton alone. A bare hydrogen nucleus, carrying a positive charge, with no electron cloud to give it size or softness or the usual repulsions that keep atoms from occupying each other's space. And these bare protons flow. That's what the simulations show, molecular dynamics calculations, including work by Cavazzoni and colleagues in 1999, where researchers modelled the behaviour of water at these extreme conditions and found that in the Superionic phase, the hydrogen moves with a diffusion rate comparable to the diffusion of molecules in ordinary liquid water. Not barely mobile, not sluggishly creeping, genuinely, measurably, liquid speed diffusion. The hydrogen in Superionic ice moves the way the water in your body moves, the way the water in a river moves, or in a glass left on a nightstand in the dark, where the molecules are always trading partners and drifting in slow circles, never still. Except that what's drifting here isn't molecules at all. It's bare nuclei, charged, fast, weaving through the gaps in a rigid crystal of oxygen that is, on its own timescale, completely motionless. Two things at once, in one material, at the same moment, solid and liquid simultaneously, in the most literal sense those words can carry. It's worth sitting with that for a moment, if you're still awake enough to sit with anything. Not just as a curiosity, not just as a strange headline, but as a real physical fact about what matter can do. We tend to think of phases, solid, liquid, gas, as categories. As boxes a thing goes into, you heat water and it moves from one box to the next, from solid to liquid to vapour, one thing at a time. But Superionic ice is not in a box. It is in two boxes at once, and it can stay there, stably, for as long as the conditions hold. It is not a transition between states. It is a state of its own. It is, in the language of materials science, a genuinely distinct thermodynamic phase. A fourth way for water to be. And because we're not rushing, and because the night is long and quiet. Let's be clear about one more thing that this phase is not. Because it's very easy to misread. Superionic ice is not slush. Slush is what you get when you haven't made up your mind about melting, when some ice crystals are still clinging to form while others have given in and turned liquid. Slush is a mixture, a mechanical blend of two phases side by side, a handful of solid chunks swimming in their own meltwater. That's not what this is. Not at all. In superionic ice, the oxygen atoms form a fully ordered, fully coherent crystal, a real lattice. Every oxygen atom in its place, every neighbour at the prescribed distance, the whole arrangement as clean and regular as any crystal you've ever seen described. If you could somehow freeze time and look at only the oxygen, you'd see a beautifully organised solid, as orderly as salt or diamond. And through that ordered lattice, invisible in our frozen moment, the hydrogen would be threading like ghosts, no fixed positions, no fixed trajectories, just a steady flow of bare protons moving through the gaps. A liquid, in all the ways that matter physically, except that it is constrained by and contained within the solid crystal around it. Two interpenetrating states, one material, not a mixture, not a compromise. A single phase that is, by physical definition, both solid and liquid at the same time. The word scientists use for it is superionic, and it turns out that word has a history of its own that's worth knowing, because it connects this strange form of ice to something you might not expect. The name superionic doesn't come from water, it comes from materials science, specifically from the study of what are called superionic conductors, or sometimes solid electrolytes. These are materials, often used in advanced battery research and fuel cell design, that conduct electricity not by moving electrons the way a copper wire does, but by moving charged ions, whole atoms or clusters of atoms with a positive or negative charge, through a crystal framework that stays solid. The framework doesn't melt, but the ions inside it move freely, like a liquid, carrying charge from place to place. It's the same physics. A rigid, solid scaffold. Mobile charged particles flowing through it. Ionic conduction rather than electronic conduction. In a metal, electricity flows because electrons, those tiny, negatively charged particles that orbit every atom, are free to drift through the material when a voltage is applied. They're already mobile in a metal. The structure of metallic bonding releases them to roam. Pull them in one direction, and you have a current. In superionic ice, the electrons are not the thing that moves. The oxygens certainly don't move. What moves is the protons, the bare hydrogen nuclei, positively charged, drifting through the oxygen lattice the way sodium ions drift through a solution of salt water. The charge is carried by atoms, not by electrons. Ionic conduction. A current made of matter, not of the charges that usually live around matter. And that is why the material ends up with the name it has. It behaves like a superionic conductor. It's just that in this case, the material is water, frozen oxygen, flowing hydrogen, which makes it more remarkable than most of the other materials in that family, and which makes the connection between a laboratory curiosity in materials science and the interior of a planet feel suddenly, quietly, strange. Now there's something else about superionic ice that's easy to overlook, partly because the solid and liquid paradox is so distracting, and partly because we don't often think carefully about density when we think about ice. Ordinary ice is lighter than water. You know this, you've seen it 1,000 times, ice floats. That little habit of ice, that ability to float in its own liquid, is one of the most quietly important physical facts in the history of life on this planet. If ice sank, winter lakes would freeze from the bottom up and kill everything in them. Instead, ice floats, insulating the water below, and life survives. The reason ice floats is that the crystalline structure of ordinary ice-ish, that hexagonal lattice, the familiar six-fold symmetry you see in snowflakes, spaces the water molecules out slightly more than they are in liquid water. The crystal has gaps in it. It's a slightly open structure which is unusual for a solid and is one of water's celebrated eccentricities. Superionic ice at 100 to 400 gigapascals of pressure has no such gaps. Under those pressures, nothing has gaps. The oxygen atoms are packed as densely as atoms can reasonably be packed, arranged in that face-centered cubic lattice we'll come back to. One of the most efficient packing arrangements in nature. And the protons, flowing through the interstitial spaces, fill in what little remains. The result is a material with a density several times that of liquid water. Not slightly denser, several times denser. You could think of it as an ice that is as unlike the ice in your freezer as glass is unlike a cloud. Both made of the same underlying thing, but transformed by pressure into something almost unrecognizably compact. This matters not just as a detail, it matters because the density of superionic ice is part of why the interiors of certain planets behave the way they do. Dense, rigid, and immense, these three properties together shape the planet around them. But we're getting slightly ahead of ourselves. The planets are the destination, and we'll walk toward them. For now, the bench, the lab, the crystal. Because there's one more piece of the bench physics to understand before we can get to the question of how anyone measured any of this at all, and that question is just beginning to form at the edge of things. Ready to unfold when we've finished here. The piece is the diamond. Why diamond? Of all the materials in the world, of all the substances a physicist might choose to build an apparatus from, why specifically diamond? Two reasons, and they run almost perfectly parallel to each other. The first reason is that diamond is the hardest material we know of. Not hard in the everyday sense of feeling hard when you tap it. Hard in the engineering sense, resistant to scratching, resistant to deformation, resistant to the crushing forces that would destroy almost anything else. When you press two diamonds against each other with enormous mechanical force, they don't crumble or deform. They hold. They transmit the load cleanly through the geometry of the apparatus, through the tapered points of the two diamond faces pressing toward each other to the tiny gap of sample caught between them. No other known material can do this at the pressures a diamond anvil cell generates and survive intact. The diamond doesn't merely participate in the experiment. It is, in some sense, the only reason the experiment is possible. But here is the second reason, and it's the one that makes diamond almost too good to be true for this purpose. Diamond is transparent. Not just to visible light, though it is extraordinarily clear to visible light, which is part of why diamonds are prized in the way they are. Diamond is also transparent to X-rays. It allows the high-energy X-ray beams used in crystallography to pass through it without absorbing them, without bending them confusingly, without interfering with the measurement in the ways that most materials would. So you can squeeze a sample between two diamonds and then simultaneously shine laser light through to heat and compress it and send an X-ray beam through to examine the crystal structure of whatever you've created, all through the same diamond walls, all at the same moment. You can look inside. In most experiments in high-pressure physics, this is the intractable problem. You can squeeze things, you can heat things, but seeing what's happening while you do it is almost impossible, because the walls of any normal containment vessel are opaque. You're working blind. The diamond anvil cell solves this completely. The walls see for you. You apply the pressure, you send in your probes, and through those transparent diamond faces you receive information back from a sample smaller than a grain of salt, sitting in conditions that match the deep interior of a planet. It is, when you think about it slowly, a remarkable kind of alchemy. Not the old kind, the hopeful fumbling of medieval scholars trying to turn lead to gold. This is alchemy with precision instruments and laser light and the hardest material on Earth. And the thing being made is not gold, it's ice. Black, burning, paradoxically solid and liquid ice, squeezed in a diamond press and lit up from outside, while it exists for a few nanoseconds in conditions no human being has ever encountered outside of a laboratory. In a room full of careful people who have spent years learning how to ask the crystal a question in the tiny sliver of time before it disappears. And that question, specifically, the question of how you photograph a crystal that destroys itself almost as fast as it forms, is exactly the one we've been letting rest, unanswered at the back of everything. You've heard it mentioned, the nanosecond window. The fact that each sample of Superionic ice exists for only a few billionths of a second before the shockwave passes, the pressure drops, and the crystal expands back into something ordinary. The birth and death of ice V, happening faster than light, can cross from one side of a room to the other. How do you see something like that? How do you take a picture of a crystal that barely exists? Hold that question gently. Don't let it trouble you. There is an answer, and it's a beautiful one, and we'll find it together just a little further along. For now, let it sit at the edge of your awareness like a lamp left burning in the next room. Warm, visible, patient, quick reminder, after years of lying awake with a racing mind. Deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. But here's where it gets stranger still. Because before we get to the answer, there's a question underneath the question. One that turns out to be even more fundamental and even more quietly astonishing. How did anyone know to look? The experiment in 2019, the one that took the photograph, the one that named Ice V and pinned down its crystal structure, that experiment happened because people already had a very good idea of what they were looking for. They had a map, and the map came not from a laboratory at all, but from a desk. In 1988, 31 years before the 2019 X-ray snapshot, 3 decades before Marius Millot and Federica Coppari stood in the laboratory for laser energetics at the University of Rochester and fired a laser at a pre-compressed drop of water, 3 scientists published a paper in Physical Review Letters. Their names were Pierfranco Demontis, Richard LeSar, and Michael L. Klein, and what they did was not an experiment in any physical sense. There were no diamonds, no lasers, no shockwaves. There was a computer. They built a mathematical model of water molecules. A simulation, what physicists call a molecular dynamics simulation, which means they described the forces between atoms in mathematical terms and then set those atoms in motion inside the computer, tracking where they went and what they did over time under different conditions of temperature and pressure. And what their simulation told them in 1988 was this: push water hard enough and heat it enough, and the hydrogen atoms will break free of their lattice positions and begin to flow even while the oxygen lattice holds. A superionic state, solid and liquid at once. It was a prediction. It sat in the scientific literature, filed away for 3 decades. Not because people doubted it, not because the math seemed wrong, but because making it happen, actually, physically, in a laboratory, generating pressures of hundreds of gigapascals and temperatures of thousands of Kelvin, was extraordinarily hard. The pressure conditions required are found essentially nowhere on Earth except deep inside its core, and recreating them, even for a billionth of a second, requires either the mechanical precision of a diamond anvil cell pushed to its limits, or the enormous localized energy of a high-power laser pulse that can drive a shockwave through the sample fast enough to spike the pressure before the whole thing flies apart. 30 years of waiting, then a prediction hanging in the air like a name nobody could quite call out. And then 2018. Then 2019. And then, at last, the ice. But before any of that happened, before the lasers and the X-ray snapshots and the formal naming of XVIII, there was already a hint. A piece of the universe quietly waiting to be noticed, somewhere out past the orbit of Saturn, in the cold dark beyond the inner planets. It's not time yet to follow that thread. Not quite. We'll get there, and when we do it, we'll feel, I think, like the thing you didn't quite realize the whole story was moving toward. For now, just let the questions stay there. The photograph. The nanosecond. The crystal that exists faster than light can cross a room. You know, when I was thinking about how to describe what this material does, how to find an image for it that might carry the strangeness without losing the truth, I kept coming back to something much simpler than any of the physics. I kept thinking about a river in winter. You've seen pictures of them, maybe. A river in deep cold, where the surface has frozen, but the water underneath is still moving. The ice above is rigid and still. You could, in theory, walk across it, or at least stand at the edge and feel how solid it is. But below that skin of ordered crystal, the water is flowing, dark and cold and continuous, moving the way water always moves, looking for the sea. 2 states of the same substance, separated by a surface you can see. The same thing happening at the same moment in the same place, just layered. Superionic ice is something like that, except that the layers aren't separated. They're interpenetrating. The frozen part and the flowing part are not stacked one above the other, they're woven through each other at the level of individual atoms. Every oxygen is part of the crystal, every hydrogen is part of the flow. And there's no surface between them, they occupy the same space. The same cubic arrangement, the same cubic centimetre of material, solid and liquid together, all the way through. It's weirder than the frozen river, more intimate, somehow more thorough. And there's something about that image, the 2 states woven together, neither winning, neither giving way, that feels true to something larger than physics. The way opposing things can inhabit the same space and not cancel each other out. The way a thing can be 2 things at once without being neither. But that's drifting into the philosophical, and you're probably getting drowsy, and there are still things to know before we move on. The last piece of the bench physics that we haven't quite touched is density, and it matters more than it might seem. Not just as a number, though the number is striking, but as a clue about where this material lives and what it does when it's there. You already know, somewhere in the comfortable half-knowledge of having lived in a world with ice in it, that ice floats. You know it because you've seen it. A cube in a glass of water, bobbing at the surface. A lake in winter with ice sitting on top and cold water sitting below. This is one of water's great peculiarities, one of the ways it refuses to behave the way most substances do. Most liquids, when they freeze, become denser than their liquid form. The crystal packs more tightly than the loose, wandering molecules of the liquid. So the solid sinks, not water. XVIII, the hexagonal crystal, the familiar form, has a slightly open structure, a lattice with small gaps built into it by the geometry of how water molecules bond to each other. That openness means the ice is slightly less dense than the liquid, so it floats. XVIII, Superionic ice, does not float. It would sink if you could somehow produce it in a glass of water, which you obviously cannot, but if you could, it would sink instantly and catastrophically, because it is compressed to several times the density of ordinary water. Not slightly denser, significantly, dramatically denser. At 100 to 400 gigapascals, the oxygen atoms are packed into a face-centered cubic lattice, one of the most efficient geometric arrangements atoms can take on, and the protons fill in the remaining spaces. There is no openness left, no gaps, no room for the structure to breathe. It's dense in the way that the rock under your feet is dense, or denser, an ice that would feel, if you could somehow hold it, like a small piece of something much larger and much heavier than its size suggests. This density is not incidental. It's why the material behaves the way it does inside the giant planets. Dense means heavy, and heavy, under gravity, means it settles. A thick, dense layer of superionic ice in a planet's interior doesn't float upward the way ordinary ice floats in a glass. It sits. It's stable. It persists. It defines the architecture of whatever lies below it and above it, the way a dense layer of rock defines the architecture of a planet's mantle. But we'll see what that means, what it looks like from the outside, what signals it sends into space that a spacecraft can measure when we get to the planets. And we will get there. The planets are the last place this story goes, and the most surprising. For now, let the bench physics settle. The diamond anvil squeezing its tiny water sample. The oxygen atoms, rigid and ordered, pinned in their positions by unimaginable pressure. The hydrogen, stripped bare, flowing through the lattice at the speed of a liquid. The crystal, hotter than lava, but still solid. The whole thing black and opaque and dense, existing in a space smaller than a grain of salt between two gem-quality diamonds in a room lit by laser light. And somewhere behind all of it, still waiting patiently, the question of the photograph. Of how you pin down the shape of something that barely exists. Of who made it, and when, and what they found when they looked. That's where we're going next. There's no hurry. The night is still long, and the story is still warm, and if you've already started to drift at the edges, if the words are beginning to blur softly into each other the way they do when sleep is close, that's perfectly fine. You'll find it all still here when you need it. The ice isn't going anywhere. So, here is the problem. You've got a crystal, a true crystal, a real, ordered, rigid thing, with its oxygen atoms sitting exactly where they belong, each one locked in precise geometric relationship to its neighbours, a face-centered cubic lattice, regular and beautiful and unmistakably solid. You've got hydrogen flowing through it like a liquid, carrying charge, making the whole thing dark and conducting and strange. You've got, in other words, something genuinely new, something that had never existed in a laboratory before. And it lasts for a few billionths of a second, not a few milliseconds, not a fraction of a breath. A few nanoseconds, a few billionths of a second, and then the shock wave has passed through the sample and the pressure begins to drop, and the crystal, having existed for the length of time it takes light to travel maybe a meter, relaxes back into ordinary matter, leaving no trace of what it briefly was. That is the problem. That's the thing that makes you sit back and think for a moment about what it even means to study something. Because in most kinds of science, the thing you're studying sits still and lets you look at it. You can turn a rock over in your hand. You can put a cell under a microscope and leave it there for hours. You can cool a magnet down and warm it back up and do the same experiment 20 times in a row, checking your results, adjusting your instruments, being careful. The object persists. That's usually part of what makes it science, the reproducibility, the patience, the ability to look again. But Superionic ice doesn't stay. It doesn't wait for you to check your calibration or adjust the detector angle. It exists, briefly, in conditions that cannot persist on the surface of any world we have access to. And then it's gone. And the question of what shape it was, of how the atoms were actually arranged, is the question of how you take a photograph of something that lasts less time than it takes a nerve signal to travel from your fingertip to your brain. And this is where the story gets, quietly, remarkable. Not loud remarkable, not the kind of remarkable you'd shout about. The gentle kind. The kind where you realize that a group of people spent years solving a problem that most of us wouldn't even recognize as a problem. The problem of time, of precision, of catching something true in a moment so narrow it barely counts as a moment at all. The answer, it turned out, was to use X-rays, not in the slow clinical way you think of when you think of an X-ray, not the kind where you hold still and breathe and wait for a technician to come back with the image. This was something far more specific. X-ray diffraction. The technique where you fire a beam of X-rays at a crystal and the X-rays bounce off the planes of atoms inside it. And from the pattern of those bounces, the angles, the intensities, the distribution of spots and arcs on a detector, you can work backward to the geometry of the crystal itself. It's a little like throwing sand at a sculpture and reading the shape of the sculpture from how the sand scatters. Indirect, but precise. And for crystals, extraordinarily powerful. It's the same technique that revealed the double helix of Dinar decades ago, in another famous case of reading shape from scatter. But to use X-ray diffraction on Superionic ice, you'd need to fire your X-ray beam at the crystal during the nanoseconds it existed. Not before, not after. During, the timing would have to be exact. The whole measurement, the creation of the crystal, the firing of the X-rays, the capture of the diffraction pattern on a detector would have to happen within a window so narrow that, if you missed it by even a small fraction, you'd get nothing but the ghost of something that had already changed back. This is where a laser facility in upstate New York becomes part of the story. The Laboratory for Laser Energetics sits on the campus of the University of Rochester, and it houses one of the more extraordinary instruments that most people have never heard of, the Omega laser. Omega is a high-energy laser system, 60 laser beams that can be focused with extraordinary precision onto a very small target, delivering enormous amounts of energy in very short, very controlled pulses. It was built for inertial confinement fusion research, the branch of physics concerned with replicating, very briefly, the conditions inside a star. But it turns out that a laser capable of driving fusion conditions is also capable of driving a shock wave through a tiny water sample and holding that shock to a tight enough pressure and temperature that you can study what the water does when it gets there. And, crucially, omega could be synchronized. The 2019 experiment, the one that answered the shape question, that named the phase, that gave Superionic ice its formal identity, used the omega laser in a specific way. The laser drove the shock through the pre-compressed water sample as planned. But at the exact moment the shock was passing through, at the precise nanosecond when the Superionic state existed, a separate pulse of X-rays was fired into the crystal, timed to within that narrow window, fired and detected in the same flash. And the diffraction pattern that came back from that X-ray pulse told them the shape. Marius Millot and Federica Coppari and their colleagues at Lawrence Livermore National Laboratory had been working toward this result for years. The paper they published in Nature in May of 2019, Nanosecond X-ray Diffraction of Shock, compressed Superionic water ice, described exactly what the X-ray snapshot showed. The oxygen atoms, frozen in their arrangement even under those conditions, formed what is called a face-centered cubic lattice, FCC for short. It's one of the most common arrangements in dense, tightly packed crystal structures, the kind of arrangement where each atom sits at the corner of a cube and at the center of each face of the cube, nestled efficiently against its neighbors. Gold does this. Copper does this. Many metals do this. And now, under the right conditions, water does this too. The face-centered cubic oxygen lattice is the structure that the name XVIII belongs to. Not a nickname, not a metaphor. A formal phase designation in the long and serious tradition of naming the distinct crystalline forms of water with Roman numerals. Ice E, which is ordinary ice, technically Ice E, hexagonal, the kind that falls from winter clouds and floats in your glass. Ice 2, discovered under pressure in the early 1900s. Ice 3, IV, V, VI, 7, and onward, each one a different arrangement of water molecules under different conditions, each one discovered by someone pressing or cooling or heating water carefully and finding that the molecules had chosen a different geometry to live in. Ice VE, the 18th named crystalline phase of water. Found in a nanosecond flash between two diamonds, photographed by a perfectly timed X-ray pulse at a facility in upstate New York by a team of physicists from a national laboratory in California. Found and named and described precisely enough that the structure could be written down and published and checked and understood, all from a measurement that was over before the sound of a gunshot would have moved a millimeter through the air. There's something I want you to sit with for a moment if you're still following this. It doesn't require any particular scientific background. It just requires the image. A crystal existed for a few billionths of a second. And in that time, human beings managed to take its picture. Not a blurry picture, not a guess, a diffraction pattern that told them precisely how the atoms were arranged, the spacing between the planes of oxygen atoms, the symmetry of the lattice, the confirmation that this was genuinely a new kind of ice and not simply an intermediate state or an artifact of their instruments. A real measurement of a real thing that barely had time to be real. And then, just as inevitably as the shockwave had created it, the crystal was gone. The pressure dropped, the hydrogen atoms that had been flowing through the oxygen lattice found themselves no longer constrained. The oxygen lattice itself relaxed and rearranged, and the Superionic ice ceased to exist, exactly as it always does when the conditions that made it are withdrawn. That's the other thing worth holding gently in mind. You cannot keep it. This isn't simply a practical limitation, a matter of needing a better container or a stronger pressure vessel. It's more fundamental than that. Superionic ice is stable only within a very specific range of pressures and temperatures, pressures that are on Earth's surface, impossible to maintain outside of a laboratory experiment lasting nanoseconds or in some cases a fraction of a second. The moment you release the pressure, the crystal doesn't just weaken or deform. It transforms. It becomes something else, ordinary water, or one of the lower pressure ice phases, or something in between, depending on how fast the pressure drops. The superionic state doesn't linger at the edge of its stability field the way some materials do, holding their form a little past where they should. It reverts, cleanly, completely, without a trace. So you cannot bottle it. You cannot bring a sample back to a shelf and examine it tomorrow. You cannot hand it to a colleague and ask them to check your work on a different instrument. Every measurement has to be made during the event. Every piece of evidence about what superionic ice is has to be gathered in real time, in the nanoseconds or microseconds of its existence, with instruments prepared in advance and synchronized to a timing that leaves no room for adjustment. And yet, people have been studying it carefully and precisely and learning more with each experiment, which is, if you think about it, a remarkable thing to have done. But here's something worth pausing on before we go further into how those experiments developed over the years. Because the measurement, the X-ray photograph, the formal naming of I6V, all of that happened in 2019. And the question that naturally rises from that is, when did anyone first think it might exist? The answer is 1988. And the gap between those two dates, 30 years roughly, is its own kind of story. In 1988, a physicist named Pierfranco Demontis, working with Richard LeSar and Michael L. Klein, published a paper in Physical Review Letters. The paper was a theoretical study, a molecular dynamics computer simulation, which is the technique of modeling the positions and motions of atoms over time using the laws of physics, letting the simulation run, and watching what the atoms do. You put water molecules into your simulation, you apply pressure and temperature. You watch. And what Demontis and LeSar and Klein saw in their simulation at high enough pressure and temperature was something unexpected. The oxygen atoms in their simulated water settled into a regular lattice and stayed there. But the hydrogen atoms, which in ordinary ice are bound to specific oxygen atoms and move with them, did something different. They detached. They began to move independently through the oxygen framework, not chaotically, not randomly bouncing around the way atoms in a gas would, but diffusing, flowing, moving through the lattice in a way that was genuinely fluid, even though the lattice itself was solid. The simulation said, under these conditions, water enters a superionic state. They published this. They described it carefully and precisely, with the mathematical signatures of the transition, the conditions at which it occurred, the behavior of the hydrogen diffusion. And then, as sometimes happens with theoretical predictions, the world moved on. The paper was noted by specialists. It sat in the literature. And for 3 decades, no one had the tools to test it. The reason was simple, and it was the same reason that always comes up when you try to replicate what happens inside a planet. The pressures involved are immense. To understand just how immense, it helps to have a reference point. The atmospheric pressure at sea level, The weight of all that air above you pressing down on the surface of the Earth is, by definition, 1 atmosphere. 100 gigapascals, which is the lower end of the pressure range needed to make superionic ice, is roughly 1 million times that. 1 million atmospheres. The pressure at the center of the Earth's core is in this range. The pressure at the boundary between the Earth's outer core and the mantle, one of the most dramatic internal boundaries in our planet, sits around 100 gigapascals. So to make superionic ice, you need to briefly exceed the pressure found at the boundary of the Earth's core. In a laboratory, in a controlled experiment, on a small enough scale that you can actually measure what happens. That's why it took until the mid-2010s for the experimental tools to catch up to the theory. The diamond anvil cell, with its gem-quality diamonds and its ability to focus pressure onto a tiny sample, had been available for decades, and it could reach very high pressures. But reaching the specific combination of pressure and temperature needed for the superionic state, and reaching it cleanly enough and long enough to make a measurement, required developments in laser technology, in X-ray sources. In timing systems, that came together gradually. The omega laser, the precision synchronization, the fast detectors. The ability to pre-compress a sample in a diamond anvil cell and then drive a shock wave through it with a separate laser pulse so you could arrive at the right pressure-temperature combination more controllably. By 2018, that combination of tools existed, and Marius Millot and Federica Coppari and their team at Lawrence Livermore National Laboratory used it. The 2018 paper, also published in Nature, was the first experimental evidence for the superionic transition. The title was direct: Experimental Evidence for Superionic Water Ice Using Shock Compression. What Millot and colleagues measured in 2018 was not yet the crystal structure, the X-ray diffraction technique that would give them the atomic geometry came a year later. What they measured in 2018 was the electrical and optical signature of the transition, the way the sample's reflectivity changed, the way it began to conduct electricity, the sharp change in behavior that said, something new has happened here. The water has crossed a boundary into a different state. That measurement was already deeply significant. It confirmed that the transition Demontis and LeSar and Klein had predicted in 1988 was real, not just a mathematical possibility, not an artifact of the simulation, but something that actually happens to water when you squeeze and heat it hard enough. The theoretical prediction had waited 30 years for someone to test it. The 2018 measurement said, it's real. And then, a year later, the 2019 measurement gave it a face. The X-ray diffraction that showed the XVIII lattice, the photograph of the atoms, the confirmation of the structure, the formal name, ICE. It's worth appreciating, in the quiet of this night, what that gap meant, not as a frustration, but as a kind of patience built into the nature of physics itself. Some things exist only in conditions we cannot maintain. Some ideas wait for the tools to test them. 30 years is not unusual in this kind of science. The prediction sat in the literature, patient and specific, waiting for a laser in upstate New York and a team in California with the right technique, the right timing, the right combination of precision and ambition. And then the tools arrived, and the prediction was tested, and it was right. That's a good thing to carry with you. The willingness to let an idea wait without abandoning it. But the story doesn't end with those two experiments. Because one of the things that the 2018 and 2019 results did was open a question about the boundary of the superionic state, about where exactly it begins. how wide its stability field is, whether there are other versions of it that haven't been seen yet. The shock compression experiments at Omega drove their samples to very high pressures, hundreds of gigapascals, the sort of pressures found deep inside giant planets. But what about lower pressures? What about the edges of the Superionic regime, where conditions are less extreme? The shock method is powerful, but it's also inherently transient. You're riding a wave, moving through a range of pressures and temperatures as the shock passes, and the conditions aren't stable in the way they'd be if you could simply hold the sample at a fixed point and study it at leisure. A different technique, static compression in a diamond anvil cell. Using a laser to heat the sample while it was being squeezed could, in principle, approach the Superionic regime from a different direction and hold a sample there long enough to study it more carefully. Not for a nanosecond, but for seconds or longer. In 2021, a team led by Vitali Prakapenka at the Advanced Photon Source at Argonne National Laboratory did exactly that. Argonne's Advanced Photon Source is one of the premier X-ray facilities in the world, a large synchrotron that generates extremely bright, tunable X-ray beams, which experimenters use to study materials in diamond anvil cells with great precision. Prakapenka and colleagues compressed a water sample in a laser-heated diamond anvil cell and found that they could reach the Superionic state at much lower pressures than the shock experiments had used, around 20 gigapascals, combined with temperatures of roughly 1,000 to 2,000 Kelvin. 20 gigapascals is still an enormous pressure by any everyday standard, about 200,000 times atmospheric pressure, but it's far less than the hundreds of gigapascals of the shock experiments. And it's a pressure that static diamond anvil cells can maintain stably for extended periods. The 2021 results, published in Nature Physics, added something else. Not just a lower pressure route to the Superionic state, but evidence of more than one Superionic structure. The face-centered cubic lattice that the 2019 X-ray diffraction had identified wasn't the only geometry. At different pressures and temperatures within the Superionic field, the oxygen atoms arranged themselves differently into a body-centered cubic structure where each oxygen atom sits at the center of a cube with one at each corner. Two distinct Superionic variants, each one the stable form under slightly different conditions, each one with its own geometry, both of them sharing the defining property of Superionic ice, the rigid oxygen framework with hydrogen flowing through it. So the map of the Superionic state turned out to be richer than the first experiments had suggested. Not a single narrow line on water's phase diagram, but a region, a territory with internal variation, with its own structural families, with more to learn. And this brings us gently to something worth pausing to appreciate. The phase diagram of water. If someone asked you how many kinds of ice there are, you'd probably say one. And in the context of daily life, you'd be right. The ice you make in a freezer, the ice that forms on a winter window, the ice that covers a lake, is all the same thing, hexagonal ice. Ice-ish in the formal notation. The water molecules arrange themselves into a hexagonal lattice, with each molecule bonded to four neighbors in a specific geometry, and the result is what you know, clear. Lighter than liquid water, fracturing cleanly, crunching under boots. But ice is one entry in a much longer list. At higher pressures, water molecules rearrange into different lattices. The bonds between molecules shift, the geometry changes. And the resulting ice, still made of water, still the same chemical formula, is a different phase with different properties, a different crystal structure, a different density, a different behavior. Squeeze ice ish hard enough, and it transforms into ice 2, which is denser and has a different arrangement of hydrogen bonds. Keep squeezing and you get ice 3, ice 4V, ice VI, and on through the series. Each one stable under its own conditions. Each one a genuine, distinct crystalline form of water. The count, as of the most recent careful surveys of the high-pressure ice literature, stands at least 20. 20 named, confirmed crystalline phases of water. And that doesn't count the amorphous ices, the glassy forms that lack long-range order, or the various ice phases that have been predicted but not yet confirmed experimentally. Ice E, the one that makes snowflakes and glaciers, sits at one corner of a phase diagram that extends across an enormous range of pressures and temperatures, and at nearly every point in that range where water is solid, it has arranged itself differently, found a new way to pack its molecules, a new lattice, a new geometry. Ice V is the most extreme of these, the one that forms under conditions that barely exist anywhere on Earth except briefly in a laboratory. The one that gave up on being made of intact water molecules at all, where the pressure was so high and the temperature so intense that the molecules themselves dissociated. The covalent bonds holding each hydrogen to its oxygen breaking apart, leaving behind a crystal of pure oxygen atoms with a fluid of bare protons threading through the gaps. The one that sits at the far edge of the phase diagram, where the map of water's behavior reaches toward the interior conditions of planets. 20 phases, at minimum. 20 different arrangements of the same 2 atoms, 1 oxygen, 2 hydrogen. Each one discovered by someone pressing or cooling or heating water to conditions it doesn't encounter in a kitchen or a cloud. Each one a reminder that what we call ice and what we call water are not the full story of what this molecule can be. The full story is stranger. And the next chapter of it, the chapter that gives all of this its weight, that explains why a nanosecond photograph between 2 diamonds in upstate New York matters for the largest worlds in our solar system, is the chapter about what's inside a planet. Not just any planet, 2 in particular. 2 that a spacecraft visited long ago and found something it couldn't fully explain. Something tilted and lopsided and wrong in a way that nothing in the existing physics quite accounted for. The planets are close now, we'll reach them soon. But for just a moment more, let the phase diagram breathe. Let it settle into something you can hold in your mind without having to grip it. 20 crystalline forms of the same substance, arranged along axes of pressure and temperature, and at the far end of that map, a phase that is both solid and liquid at once, that cannot be kept or carried or examined after the fact, that lasts for nanoseconds and has its photograph taken by X-rays timed to within. That window that was predicted in 1988 and first made in a way that could be confirmed and named in 2019. And let the quiet of it rest there with you. The fact that water, the water in your blood, in the glass on your bedside table if you have one, in the clouds and the ice and the rain outside, is not one thing but many. That the molecule you learned as H2O, 2 hydrogens and an oxygen, simple and familiar, is capable of arrangements that would be unrecognizable to anyone who only knew ice-ish. That the same atoms, depending on where they are and how much pressure surrounds them, and how hot or cold the environment is, can build something clear and hexagonal and light enough to float, or something black and dense and hot, with its hydrogens stripped free and flowing like a river through a crystal frame that doesn't move. The ice in your glass is one end of the story. Ice XVIII is the other end. And somewhere between those two extremes, out past the orbit of Saturn, in the cold dark of the outer solar system, where two blue planets turn slowly in the faint sunlight, is where the story finds its destination. And so that is where we go next. Gently, no rush. Out into the dark, past Mars and past the asteroid belt, and past Jupiter with its great storm, and past Saturn with its rings, past all of that, out to where the sunlight has thinned to something faint and cold, and where two planets drift in orbits so far from ours that even light, travelling at the speed light travels, takes more than 4 hours to make the crossing. Uranus and Neptune. You may know them as the blue planets, the distant ones, the ones Voyager 2 visited, the only spacecraft ever to do so, and then left behind. They sit out there right now, as you listen, turning slowly, wrapped in cold methane haze that gives them their colour. Two worlds so remote that we have sent exactly one piece of human machinery past both of them, and that was decades ago. And here is the thing about them that matters for our story. They are not made of what their name suggests. We call them ice giants, and the name is accurate in a technical sense, but it is misleading in the everyday sense. When most people hear ice giant, they picture something vast and frozen. A planet-sized snowball, perhaps, or a globe of clear blue ice, cold all the way through. But that is not what Uranus and Neptune are. They are not frozen, not in any sense you would recognize. Roughly 80% of the mass of each of these planets is what planetary scientists call an icy mantle. But that mantle is not cold, it is not slow, it is not what you would picture. It is a hot, dense fluid, a pressurized, superheated mixture of water mostly, with methane and ammonia folded in, sitting at pressures of millions of atmospheres and temperatures of thousands of Kelvin. It is less like a snowball and more like a very strange, very compressed, very hot ocean that goes all the way down. And as you sit with that picture, a scalding, crushing fluid mantle, millions of atmospheres, thousands of degrees, you may recognize where that description is pointing. It is pointing directly at the phase diagram. It is pointing directly at the conditions where ice XVIII is stable. The pressure-temperature window where Superionic ice exists, roughly 100 gigapascals and up, temperatures of 2000 to 5000 Kelvin and beyond, is precisely the window you find inside the deep interiors of Uranus and Neptune. Not approximately. Not in a loose, hand-waving way. The numbers line up. The experiments that created ice XVIII in the laboratory. The shock-compressed samples at Lawrence Livermore and the laser-heated diamond anvil runs at Argonne, those experiments were not inventing a new substance from scratch. They were reaching, for nanoseconds or for brief heated moments, the conditions that exist permanently, stably, continuously, right now, inside both of those planets. Permanently, not for nanoseconds. Not for a flash too brief to photograph without a timed X-ray pulse. But for as long as those planets have been the size they are, which is billions of years. The ice giant mantles do not last for a few billionths of a second and then release the pressure and revert. They sit under the weight of the planets above them. They have no release valve. The pressure does not ease. And so the water in those mantles, the vast majority of the mass of both Uranus and Neptune, is very likely sitting permanently in the Superionic phase. Not a thin film of it. Not a brief layer. A vast, thick shell. Planet-sized quantities of ice XVIII, with its oxygen atoms locked into rigid face-centered cubic lattices, and its hydrogen atoms, its protons, stripped bare, moving at liquid-like speeds, streaming continuously through those lattices, conducting electricity, carrying charge, behaving like a fluid while the oxygen frame around them holds perfectly still. Planet loads of it. 2 planets, tens of thousands of kilometers in diameter, their interiors dominated by a phase of water that could not be confirmed to exist until 2019. That exists in the laboratory for nanoseconds, and that may have been sitting inside those 2 worlds for the entire age of the solar system. Let that settle, just for a moment. The diamond anvil, the laser, the 2 gems pressing on a single droplet. The nanosecond window, Marius Millot and Federica Coppari timing the X-ray flash to within that window and catching the photograph of the face-centered cubic oxygen lattice. All of that exquisite, difficult, precise work, it was not creating something new. It was visiting a place that already existed. It was reproducing, for 1/1000th of a second, the permanent interior of 2 worlds in the outer solar system, which makes the lab feel different, somehow, when you think of it that way. And then there is Voyager 2. The mission launched in August 1977. 2 spacecraft, Voyager 1 and Voyager 2, sent on a grand tour of the outer solar system. The 2 launched on slightly different trajectories, designed to use the gravity of each planet to slingshot them to the next. A once in every 175 years alignment of the outer planets that made the whole journey possible. Voyager 1 went past Jupiter and Saturn. Voyager 2 did too, and then kept going. In January 1986, Voyager 2 reached Uranus. It was the first spacecraft ever to fly past that planet. It would remain the only one for decades, for all the decades since actually, right up until this moment while you listen. And as it flew past, it measured things. Its instruments took readings of the magnetic field. What it found was strange. Not subtly strange. Dramatically, obviously, deeply strange. The magnetic fields of most planets we understand are reasonably tidy. Earth's magnetic field is roughly aligned with its rotation axis, off by about 11 degrees, which is why a compass doesn't point exactly to the geographic North Pole, but close enough. Jupiter and Saturn have fields that are similarly well behaved, roughly centered on the planet, roughly aligned with the spin axis, the kind of field you would expect from a planet-sized dynamo working the way dynamos are supposed to work. Uranus's field was nothing like that. Voyager 2 found that the magnetic field of Uranus is tilted from the rotation axis by about 59 degrees. More than half a right angle. Not a slight lean, a dramatic tilt, as if someone had taken the planet's magnetic north and shoved it sideways by more than halfway toward the equator. And not only tilted, but offset, the center of the field is not at the center of the planet. It is displaced from the planet's center, sitting off to one side. Then, 3.5 years later, in August 1989, Voyager 2 reached Neptune, and found the same thing. Neptune's magnetic field, tilted about 47 degrees from the rotation axis, also offset from the planet's center, also lopsided, also nothing like the neat-centered field of a well-behaved planetary dynamo. 2 planets, both with strange tilted off-center magnetic fields, neither of them like anything in the inner solar system. Both of them the ice giants, both of them the ones with the icy mantles, both of them the ones whose interiors, it would turn out, though Voyager didn't know this yet, because it was 1989 and the Superionic phase wouldn't be confirmed for another 29 years, hit exactly the pressure-temperature conditions where Superionic ice lives. The question Voyager 2 left behind was not a small one. Why are the magnetic fields of both ice giants tilted and lopsided when every other planet we've visited is not? It sat there for decades. Not unanswered exactly. People had hypotheses, people had ideas, but not explained at any deep level. The ice giants were strange, their fields were strange, and without knowing what was actually inside them, without any way to reach those interiors, the question remained open. And then, in the years after the 2018 and 2019 Superionic ice experiments, something shifted. Because now there was a candidate answer. The way magnetic fields are generated inside planets involves something called a dynamo. Not a dynamo in the mechanical sense, not a generator with wires and coils, but a process. A layer of electrically conducting fluid, moving and churning, driven by heat flowing outward from the planet's interior, generating magnetic field lines the way flowing charged fluid always does. The Earth's dynamo is thought to sit in the liquid outer core, an ocean of molten iron and nickel that circulates in complex patterns and produces the field a compass responds to. Jupiter's dynamo sits in a layer of metallic hydrogen deep inside the planet. Saturn's too. The key ingredient is motion. The conducting fluid has to move, it has to convect, to have warmer material rising and cooler material falling. Circulation carrying the charge through the magnetic field, amplifying it, sustaining it. A static layer of conducting material doesn't make a planet-sized dynamo. You need the churning. Now think about a deep layer of superionic ice. The oxygen sublattice is not churning. It is a rigid crystal. It does not convect. It cannot. The structure is locked. The oxygen atoms, sitting in their face, centered cubic positions, fixed in place by the pressure. You cannot have convective circulation in a crystal. The heat can conduct through it, but the material itself doesn't flow the way a liquid mantle does. Which means a deep, thick layer of superionic ice inside a planet would be, magnetically speaking, inert. It would be a barrier. It would sit there, rigid, not generating a dynamo, not churning, just, present, a giant solid crystal shell, conducting electricity because of the protons streaming through it, but not convecting, not doing the churning that a planet-scale dynamo requires. And outside that rigid layer, above it, closer to the surface, you would have the upper regions of the mantle, where the pressures are lower, where the conditions are not quite those of the superionic phase, where the material is genuinely liquid or ionic fluid and could convect. A thin outer shell of conducting fluid, moving, churning, generating a magnetic field. But only a thin shell, not the deep, planet-spanning dynamo that produces a neat centered field. Thin shell dynamos, it turns out, behave differently than deep ones. They produce fields that are tilted, offset from center, lopsided, not aligned with the rotation axis. The mathematical and physical reasoning for this was worked out by Sabine Stanley and Jeremy Bloxham. Their models, published in 2004 and 2006, showed that confining the dynamo to a thin outer shell naturally produces exactly the kind of tilted, off-center fields that Voyager 2 had measured. And then superionic ice provided a reason why the dynamo might be confined to a thin shell. Not in a speculative way, in a mechanically specific way. A deep, rigid superionic layer that won't convect. An outer conducting fluid layer that can. Confine the dynamo to the outer layer and you get a tilted, lopsided field. Which is what you see. This is the leading explanation for the magnetic fields of Uranus and Neptune. It is a hypothesis, a very well-supported one, physically coherent, consistent with everything Voyager measured, consistent with the laboratory properties of superionic ice, but it remains a hypothesis because no spacecraft has ever descended into those mantles. No probe has sampled those pressures and temperatures directly. No instrument has confirmed that Superionic ice is sitting down there the way the models predict. It is, as scientists sometimes say when they are being precise, compelling but unconfirmed. Still, think about the shape of it. Voyager 2 flies past Uranus in January 1986 and measures a magnetic field that is tilted 59 degrees and sitting off-center. It files the mystery away, files it under strange planets, unexplained. 3 years later it flies past Neptune, same strange field, 47 degrees offset from center. Files that one away too. Decades pass. The outer solar system waits. And in 2019, on the other side of everything, in a laboratory at Lawrence Livermore National Laboratory, a laser hits a pre-compressed droplet of water between two diamonds. A shockwave spikes the pressure to hundreds of gigapascals. The temperature reaches thousands of Kelvin. And for a few billionths of a second, the water arranges itself into a face-centered cubic oxygen lattice with protons streaming freely through it. The Omega laser at the University of Rochester fires its timed X-ray pulse. The diffraction pattern appears. Marius Millot and Federica Coppari and their collaborators look at what the X-rays have drawn. And the two halves, the Voyager mystery and the diamond anvil flash, begin to fit together. Not perfectly, not yet, not with the certainty that a direct measurement would bring, but fit. The way two pieces of a puzzle fit when you have been looking for them for a long time. There is one more thing to mention before we come to the end. Just one. Uranus and Neptune are cold by surface standards. The atmosphere of Uranus hovers around -200 degrees Celsius in its upper cloud layers, which is why the planet radiates almost no heat of its own at all. A strange quirk that makes it unusual even among ice giants. But in the deep interior, under all that pressure, the temperatures are thousands of degrees. And those pressures do other things besides make Superionic ice. Methane, which is present in the icy mantles, along with water and ammonia, behaves very strangely under extreme compression. When the pressures climb high enough and the temperatures are high enough, the carbon-hydrogen bonds in methane can break. The carbon atoms, freed from their molecules, can be squeezed so hard that they crystallize into diamonds, real diamonds, falling through the liquid interior of the planet, sinking toward the core, growing as they fall. It is called diamond rain, and it was experimentally demonstrated in 2017 by a team at SLAC National Accelerator Laboratory using laser-compressed polystyrene as a stand-in for the interior of the ice giants. The carbon atoms crystallized, small diamonds formed. The experiment worked. The interior of Uranus and Neptune is, according to models, a place where it rains diamonds. That is a separate phenomenon from the Superionic ice, a different material, a different mechanism, a different phase transition. But it happens in the same extreme environment. The same pressure and temperature ranges that create ice XVIII also destroy methane and crystallize its carbon into gems. The interior of those two planets is not one strange thing. It is several strange things, layered and coexisting, all of them born from the same crushing, scorching conditions. Superionic ice and diamond rain and ionic fluid and heat flowing slowly outward through materials that behave like nothing in the world you can hold in your hand. And now we reach the end of the story. Or what might be the end, or what might, if you turn it around, be a kind of beginning of a new way of seeing. because here is what I want to leave you with as you settle wherever you are. As the lamp dims, or the room quiets, or the sounds outside slow down. When you think of ice, you probably think of what you know. The ice in a glass of water, the frost on a window on a cold morning, the ice rink, the glacier, the snowflake. Clear, hexagonal, ordinary, the thing that floats because it is less dense than liquid water. A quirk of chemistry you probably learned in school. Ice, the ice you have always known. That ice, your ice, the transparent floating kind, exists in a very narrow window of the universe's phase diagram. It requires temperatures near or below 0 degrees Celsius. It requires pressures near or below 1 atmosphere. It requires the thin, temperate skin of a small rocky planet in a fairly comfortable orbit around a medium-sized star. It requires conditions that, on a cosmic scale, are rare. The universe is not mostly made of thin, temperate skins. The universe is mostly made of the interiors of things, the deep, crushing, scalding insides of giant planets and their even larger cousins across the galaxy. Water-rich worlds, and there appear to be many of them, because water is not exotic. Because hydrogen and oxygen are among the most common elements in the universe, and they combine, those worlds carry their water not at the surface, not in gentle lakes or morning frost, but under enormous pressure, at enormous temperature, in the phase that Demontis and LeSar and Klein predicted in 1988, and that Millot and Coppari first pinned down in 2019. Superionic ice. Black, dense, hot, rigid in its oxygen lattice, fluid in its hydrogen currents. Not a curiosity. Not a laboratory oddity created briefly between 2 diamonds for a nanosecond and then gone. A permanent state, a resting condition. The phase that water settles into when the pressure is high enough and the heat is high enough, which is to say when things are the way they usually are, deep inside large planets in the outer solar system, and probably deep inside the innumerable water-rich worlds orbiting innumerable stars in every direction from here. Some of the researchers who have worked on Superionic ice, Millot and Coppari among them, have suggested, carefully, that when you consider the probability, when you consider how many giant planets and ice giant worlds and super-Earths and water worlds likely exist across the galaxy, it may be that Superionic ice is among the most abundant forms of water in the universe, not the rarest, not the most exotic, among the most common. Which makes ordinary ice the exotic one, which makes the ice in your glass and the ice in the clouds above you, and the ice caps at the poles, and every snowflake that has ever fallen, a strange provincial thing. A form of water that requires the very specific, very unusual conditions of a small temperate world. A form that the vast majority of the universe's water never experiences, because the vast majority of the universe's water is not near the surface of a small temperate world. It is deep inside something enormous, under pressures that would crush any container you could imagine, at temperatures that would incinerate any material you have ever touched. It is ice V. It is the default. And we didn't know that until 2019, when a laser fired at a diamond-squeezed droplet of water and the X-rays drew the picture of a face-centered cubic oxygen lattice that had been predicted for 31 years and had never been seen. You are made of water, not of Superionic ice. Your pressures and your temperatures are nowhere near those conditions. And that is something to be quietly grateful for. But you are made of the same molecule. Hydrogen and oxygen, 2 atoms bonded into a V shape, 3 atoms in a 3-atom arrangement that turns out to be capable of at least 20 solid crystalline forms, and at least one phase that is both solid and liquid simultaneously. You carry that molecule in your blood and your cells, and the slow, quiet chemical processes that happen in your body right now, in the dark, while you breathe, while your eyes grow heavy. The water in you is the rare kind, the temperate kind, the kind that floats and flows and nourishes, and has been called the universal solvent because it dissolves so many things so well. The kind that makes life possible, on this particular planet, in this particular orbital window, around this particular star. Out past Neptune, billions of kilometers from here, water is something else. Something rigid and black and hot, with hydrogen running like a river through a crystal that does not move. Something that has been there since those planets formed, since the outer solar system settled into its current shape billions of years ago, since before there were eyes anywhere to look at it. And we reached it for 1 nanosecond in a laboratory. We reproduced it, briefly, between 2 diamonds and a laser pulse. We took its picture with X-rays timed to within that nanosecond window. We named it. We added it to the phase diagram at the far end, past all the other numbered ices, at the place marked XVIII. We built a door to it, in other words, even if we could only hold it open for a billionth of a second. And through that door, for that nanosecond, we looked out at the permanent interior of 2 worlds that only one spacecraft has ever visited. And we recognized what was there. That recognition, the laboratory and the planet touching for a nanosecond, feels like something worth carrying into sleep, not as a fact to hold tightly or an equation to remember, just as a shape. The shape of a thing that was predicted and waited and was finally seen. The shape of 2 planets turning slowly in the dark with their strange tilted magnetic fields, and the ice inside them that might explain those fields, and the 31 years between the prediction and the confirmation, and the nanosecond in which the confirmation happened. Things take the time they take. The universe keeps its secrets for as long as it keeps them, and then, one day, someone fires a laser at a droplet of water between 2 diamonds, and the picture comes through. That is where we are in this story. The picture has come through. The phase exists. The map has ice XVIII on it now. At the far end, where the pressure is millions of atmospheres and the temperature is thousands of Kelvin, and the oxygen is rigid and the hydrogen flows. It is there. And the ice giants are out there too. Still turning, still wearing their tilted magnetic fields. Still, if the models are right and the hypothesis holds, wrapped around vast silent mantles of the strangest ice anyone has ever made. They will be there when you wake. There is no urgency. No final answer you missed. No equation that slipped by while you drifted. The phase diagram will still have 20+ entries tomorrow morning. The diamond anvil cell will still work the same way. The Omega laser will still exist at the University of Rochester. Marius Millot and Federica Coppari's 2019 paper will still be in the journal. Voyager 2's measurements from January 1986 and August 1989 will still say what they say. Uranus will still have its 59-degree tilt. Neptune its 47. The Superionic layer, if it is there, will still be there. None of it is going anywhere. Wherever you are right now, whatever city or town or countryside, whatever bed or couch or quiet corner, the water in you is still water, moving and ordinary and remarkable in its own right. And out past the dark, past the distances that take years to cross even at the speed of light, the other kind waits. Both are real, both are water, both are H2O. 2 hydrogens, 1 oxygen, depending entirely on the pressure and the temperature, either the floating, familiar ice in your glass or the black, scorching, dual-state crystal at the heart of a world we have visited exactly once, briefly, decades ago. That's the molecule, that's what it can be. And I think that is a good thing to carry into sleep. Not a problem to solve, not a mystery to finish. The mystery has been, at least partly, solved, and you have heard the solving of it, slowly, here, just the shape of it. The range of it, the fact that one ordinary, familiar molecule, the one in clouds and rain and blood and morning coffee, turns out to reach, at its other extreme, into a crystal that has its photograph taken for a nanosecond between 2 diamonds before vanishing forever back into ordinary pressure and ordinary temperature and ordinary ice. The ordinary is extraordinary. It always was. If you enjoyed travelling through this slow, strange corner of physics, and if you'd like to keep these journeys coming, a like and a subscribe means a great deal. Small creators like me rely on your support to keep exploring, to keep going slowly through things that deserve more than a hurried look. And if you want to leave a note before you sleep, I'd love to know, where in the world are you listening from tonight? And what time is it in your corner of the dark? Thank you, truly, for being here, for staying this long, for letting Superionic ice be the last thing you thought about before your eyes closed. Sleep well, fellow Voyager. The next journey keeps until you wake.